In this video, we're going to look at equilibria of a force function and talk about stable and unstable equilibria. So first of all, what do we even mean when we say an equilibrium? Well, an equilibrium point is where an object comes to rest, essentially. That's kind of an oversimplification, but it's good enough for us. It's basically where there's no forces acting on the object at that point. So there are kind of two types of equilibria. So let's suppose a ball was rolling along this curve. It could come to rest in one of two places. It might come to rest at the bottom, or it might come to rest at the top of this hill. Now, if it's at the bottom, so these are both equilibrium points. Now, if I were to nudge the ball a little bit while it's at the bottom of the hill, it would kind of roll back to the bottom of the hill. So we're going to call this a stable equilibrium, because if you nudge it a little bit, it will return back to that equilibrium point, or at least not go very far away from it. But if the ball's on the top of the hill and we nudge it a little bit, then it's going to roll down the hill and go somewhere completely different. So we would call that an unstable equilibrium point. So equilibrium points do relate to what we're doing in vector calculus because, well, let's remember, if we have a force function f, and if it's a conservative vector field, then it is the negative gradient of some potential function v. And basically, the equilibria of f are the critical points of v, and that makes all sorts of sense because the critical points of the critical points of v are going to be where the gradient equals 0. Well, that's where f's going to equal 0 because f is the negative gradient. And the stable equilibria points, or equilibrium points, are going to be the local minimums of v. So that's kind of where, if you think of this sort of as our potential function, it makes sense that it would be the minimums because anywhere else you go, you're at a higher potential. So let's go ahead and do an example here. So we have a function f, or a vector field f, negative 6x minus 2y minus 2i, plus negative 2x minus 4y plus 2j. We want to show that f is conservative with potential function v given here. All that means is we want to show that f equals the negative gradient of v. So let's find the negative gradient of v. That's going to be negative, well, what's the gradient of v? Well, the partial in respect to x is going to be 6x plus 2y plus 2. And the derivative in respect to y is going to be 2x plus 4y minus 2. Distributing that negative sign, we're going to get, so this is negative gradient of v. And that's also going to be equal, distributing that negative, as negative 6x minus 2y minus 2. And then negative 2x minus 4y plus 2. So, and that is exactly what f equals. So we've shown that f is conservative with potential function v because the negative gradient of v equals f. Now we want to find the equilibrium points and see if it's stable. So we want to be a little careful here. We have our vector field here. We have our potential function here. And it would be really tempting to just skip taking the gradient and use f, but remember f is the negative gradient. So, and we're going to be trying to find the critical points. Using the negative gradient won't affect our critical points, but it will affect our local maxima and minima. So let's just take a moment and write out that the gradient of v, which is what we're really going to be using, is positive 6x plus 2y plus 2, and then 2x plus 4y minus 2. So we want to set that equal to 0. That's going to get us a nice little system of equations. I'll do a little bit of solving initially. So we're going to have 6x plus 2y equals negative 2. I just moved the 2 to the other side. And then we're going to have 2x plus 4y equals positive 2. I could probably do some shenanigans with matrices, but I'm just going to do this by elimination the old-fashioned way. Maybe do the first equation times -2 times the second. That will get me -10, so we'll multiply this by -2 just for fun. That's going to get me -12x minus 4y equals 4, and then 2x plus 4y equals 2. Add those together to get -10x equals 6. Divide both sides by -10. We're going to get that x equals -3/5. Go back to one of our equations to solve for y. Maybe we'll use this one. We'll have 2 times -3/5 plus 4y equals 2. Maybe multiply by 5 just to clear some stuff out. That's going to be -6 plus 20y equals 10. Add 6 to both sides. We're going to get 20y equals 16. Divide both sides by 2. We should get y equals, or by 20. How about 20 instead of 2? And we will get y equals 4/5. So we have an equilibrium point, and the only equilibrium point is going to be at -3/5, 4/5. Now, if I want to show that this is a stable equilibrium, I need to show this is a minimum of v. So minimum, if we want to do that, we're going to need to calculate the Hessian of f, or of v, I should say. Definitely want it to be a v because, as we said, if we use f, we're doing a couple things wrong. And we're going to look at the sequence of principal minors. So if we do that, we're going to get that the Hessian of v equals, first let's take the partials of the first function. That's going to be 6, and then 2. Then we'll take the partials for the second function. That will be 2 and 4. Our first minor, my d1 value is just going to be 6. My d2 value is going to be 24 minus 4, the determinant of the whole matrix, which is 20. Since each term of the sequence of partial minors is greater than 0, this tells us that v has a local min at -3/5, 4/5. Which then tells us, I'll scroll down slightly just so we can write it. Therefore, since it's a minimum of the potential function, therefore, -3/5, 4/5 is a stable equilibrium point. So that's it. Just to recap, we started by showing that our function f, our vector field, was conservative with a potential function. And then we used that potential function to find the critical points by setting the gradient equal to 0. That itself was just the same as setting our force function equal to 0, finding whether there's 0 forces acting on stuff. But then we had to go an extra step, showing that we had a minimum of the potential function to show that we had stable equilibrium. And that's a little different. We weren't able to get away with just using the force. We had to make sure that we did, in fact, factor in that extra negative sign. So, but yeah, so to show that we had a stable equilibrium, we just showed that negative 3/5, 4/5 was a local minimum of the potential function, which is something that we can do using other stuff we've learned in this class. So there you go.